Okay, here we go. Here we are in the second part of Chapter 2. To be or not to be? That is the question. Ha! Okay, let's move on. So here in Chapter 2b, we are looking at energy and matter. And energy, if you think about it, is the ability to do work. Being able to push something, pull something, pick up something. You know, all those things are resort to some kind of energy that's involved. Now, there's 6 common forms of energy out there. One is mechanical. Most people are familiar with it, like kinetic energy and potential energy. Energy of motion, potential, energy of position. Those would all be examples of mechanical energy. Okay, thermal energy. Think about meow, little kitty there. And what is the coldest and what is the hottest areas on the kitty cat? Okay. And then there is acoustic, which is sound. So you could sit there and look at singing or okay, playing the guitar. Those would be examples of acoustic energy. So with that, we also have electromagnetic energy. Now that can come in a lot of forms. You can think about using your microwave. Whatever you decide to, oh my gosh, I have a life, I gotta use my cell phone. Or I gotta scroll to go and find out my update. Ooh, I got 5 likes. Oh, my life has changed. Okay. Oh, look, Instagram, Snapchat, or whatever possible social media outlets there are out there. Now, there is also chemical energy, which you can look at things of natural gas being lit up and flaming away. And you can cook stuff or heat things. Then you have nuclear energy with Mr. Happy on here. Okay, so those are our 6 basic forms of energy out there. Now, we got to look at thermodynamics. Exactly what is thermodynamics? It's a branch of chemistry. It studies movement and conversion of energy. Now, it also extends into physics as well, interestingly enough. Now, there's a few laws of thermodynamics that we get to work with. There's 3 of them we're going to work with here in regular chem and honors chem. The first one is the law of energy conservation, where energy cannot be created or destroyed. However, it is converted from one form to another. You'd say, well, wait a minute, what do you mean by that? Well, we can look at something like taking our cell phones, for example, and it's like, oh my, I only got 15% of my battery left. I gotta go recharge it. Well, what's up with that? Well, you're gonna take your recharger, stick the cord into the phone, and plug it into the wall. Well, what are you doing? You're taking electrical energy, you're putting it into the battery, you are having the battery go backwards, you're recharging the battery, so you're making some changes there. Okay, electrical energy into chemical energy. Chemical energy being in the battery. Another way to look at this in terms of change of energy, think about this. Here you are talking to your friend. Hi. You have sound energy goes into the phone, which changes it to electrical energy that gets transmitted to a type of radio energy, radio waves, electromagnetic, and it goes to the cell phone tower, transfers to the other side, and then it comes back to your friend's phone. Your friend's phone now goes from radio waves into electrical impulses, which then changes those electrical energy, those impulses, into sound energy. So when you say, hi, your friend ends up getting, through all those energy changes, hi. Oh, hey dude, what's up, yo? Right, so those are energy changes. They can't be created, can't be destroyed, but definitely changes from one form to another. Now there is the second law of thermodynamics, also known as entropy. Okay? Now the reality is entropy, it is an increasing in the disorder of things. You are losing energy, you're losing organization. All natural processes tend toward the highest entropy, in other words, the least amount of order, and the minimum usable energy. And entropy naturally increases. Well, what do we mean if you think about it? look at an ice cube. Minimum entropy, maximum order. Okay, and then after a while, you get a puddle of water. There is no structure, so you don't have any order. There's minimum order, but there is maximum entropy. In other words, the energy is not particularly usable. I like this illustration as well, but there's a disorganization. Our first letter here and our last letter here, very, very different. Entropy tends to be the running down of things. So at the, in the morning when you wake up and you're ready to go to school because you're excited about chemistry, woo! You are full of energy. Yeah, just like I am here in the beginning of July. Yeah, okay. And then by the end of the day, you're like, oh, I can barely make it. And that's it. There's your entropy in the real world. Real chem, real fast. All right, let's move on here. So we got to talk about the particle model of matter. Now, okay, what's up with this particle thing? Well, all matter is consisting of tiny particles. Remember, we talked about particles being atoms or molecules, or atoms and molecules together. So we call them particles. It makes it a lot easier, okay? And they'll move and they collide randomly. That's what's going on with them. And diffusion is particles spreading apart, okay? Like perfume in a room. You walk into a room, you're talking with your friends, then from the other end of the room, somebody steps in and you know within 10 seconds they're wearing the worst, cheapest perfume or cologne, whatever applies to you, ever. Because you're smelling it and they're like 30 feet away from you, but you're dying, okay? It wasn't like that before they got into the room, but when they got into the room, baby, yeah, within seconds, you're like, oh. That's diffusion. Real chem, real fast. Now, there's also kinetic energy. We looked at how particles can move around, okay? But there's kinetic energy. Particles of matter are in constant motion. Now, it could be lots and lots of motion or just barely moving, okay? But there's kinetic energy in here, where we have our basic formula here. Kinetic energy equals 1/2 times the mass of the object times the velocity of the object squared. And that gets us in joule, which is the unit of energy. So we have an artillery piece here firing. Okay, that's kinetic energy. See the little thing coming out of the gun there? Here's a dog chasing a cat. There's kinetic energy because it's moving energy. And then here we got a volleyball player just about to spike it into the face of that poor unsuspecting soul on the other end. Okay, that's not entirely true about the unsuspecting part, but you get the idea. So we looked at kinetic energy. It's moving energy. Now, what about the internal energy of an object? Because all objects have energy in them. Some of it is moving energy, some of it is stored up. And that's where potential energy is. So when we look at potential and kinetic energies of the object's particles, that's the internal energy of the object. Now, if we were to just focus on the thermal energy, that's the kinetic energy of an object's particles. That funny little symbol that you see there that looks like a big M that's been tilted on its side, okay, that's called sigma. Sorry, did I get that right? It's the summation of. I think the math teachers will correct me on that one. But this just basically means it's the summation of. So internal energy of an object, it's the summation of potential plus kinetic energies of the object's particles. Thermal energy, we look at the summation of the kinetic energy of an object's particles. Temperature, on the other hand, is the average kinetic energy of a system's particles. Now, it could be an object or it could be something else, depending. Okay? So, inevitably, we know, because of basic thermodynamics, that energy is going to move around. It's going to transfer from one place to another. Okay, it's going to get converted to one thing to another. So we look at heat transfer. That's the transfer of thermal energy between two objects or substances. Well, stop and think about it. If this wasn't possible, we couldn't cook our food. We couldn't sit there and barbecue, for example. Like Grumesticcio! Yeah, that's right. I do grill. Old school, baby. Not that gas nonsense. Charcoal all the way. For the win, I might add. Real chem, real fast. So that's heat transfer. You're having the heat go from the stove to the pan. From the pan into the egg. That's how we cook our food. Okay? Now, heat is the quantity of thermal energy transferred from one object to another. And here's the kicker, guys. Heat is not the same as temperature. So here, for example, we've got 2 glasses of water. One definitely has more water than the other. Now, they are both at the same temperature. The question is, which one has more heat energy in it? Well, if you think about it, if they have the same temperature, one is bigger than the other, it has to have more heat content in it compared to the smaller one. Even though the average amount of kinetic energy is the same, this is still, there's more of this. Let's say this has a value of a heat value of 1 to get this temperature. If you put a heat value 1 here, is that temperature going to go up, down, or stay the same? Now remember, there's more water, and you only got a heat value of 1. Okay? That's like 1 piece of pizza for 3 people. 1 piece of pizza for 12 people. Do the math. What would you rather have? Shoot, I'd be going for the 1 pizza for the 3 people. Yeah, for the win. Okay. Moving on. So, we're looking at energy. We know that energy moves around. We know the difference between temperature and heat. Okay? But now we have to look at what's going on with processes. There are chemical reactions, but there's also physical processes that involve the energy moving around. Okay? And in some cases, the energy is either going to leave or the energy is going to be picked up. It's going to be absorbed. Okay? So that's where we talk about exothermic and endothermic. It can apply to reactions, but it can also apply to processes as well. So exothermic, let's break down the word. Thermic having to do with thermometer, thermal energy. So that probably has something to do with heat. Exo, think Exodus. What were the people, the children of Israel doing? They were exiting Egypt, weren't they? They were on an exodus. They named a book of the Bible as a result of it. They call it, so exothermic. Exoskeleton, think of the exoskeleton in biology of the bugs. You know, when you step on the beetle and you hear that distinctive crunch like you stepped on a potato chip. Yeah, let that stick in your mind for a while. But exothermic, that means it's giving the energy away. And usually people will sit there and think, kaboom, explosions. That's true. That is one kind of thing. Now what about a hand warmer? Okay? That's also something where you have an exothermic reaction. But what about this? Well, wait, what's with the ice cubes? When you're freezing water to form ice, where is the energy in the water going to go? Is it going to absorb it, or is it going to let it go, let it go? Exothermic, don't you see? Let it be. The water's got to let that energy go. Okay? And that's the idea behind freezers, because it sucks the heat energy out of the food that you're freezing or the water to form those awesome ice cubes so your soda can be cool. All right. Endothermic is the exact opposite. It's absorbing energy from the surroundings. So the whole point about ice cubes being in your cup of soda, make the soda cold. Duh. Okay, how does it do that? It absorbs the heat energy from the soda, dropping that temperature. Okay, here we got somebody there with a boo-boo on the arm. You put an ice pack on there. What's the point of the ice pack? Come on, athletes, talk to me here. Right, it's going to absorb the heat from the boo-boo area of the body. What does that do? It makes the blood vessels shrink a little bit so you're not dealing with the swelling issues that your body normally would have when you get that kind of a boo-boo on there. So endothermic and exothermic. We are going to do an experiment regarding this. It's going to be awesome. Okay. In order to get at it, we still got to talk about temperature scales, and I got to look at my timing. Oh, crud. Already 15? Okay. Maybe I'm just going to have to make this one stop here. Okay, so I am going to stop here, and I'm going to have to do a third one talking about temperature scales. Okay? I'm going to stop right here, boys and girls, but there is a part 3. Stay tuned.